we move to the next paper, and this paper is called Conformalized Density-based Clustering Analysis of Malicious Traffic for Botnet Detection, and is going to be given by Baharen Muhammad Kiani, and I believe this talk is being recorded.
Yeah. Wait a moment. Okay, we are encountering some technical problems, so wait a minute.
Hello, I will talk today about my work in which I present a clustering technique within the conformal prediction framework and describe the application to bot-generated network traffic in order to build botnet behavioral models with a view to improving the detection of compromised hosts.
Right, guys. Yeah, we're trying to sort it out. Of course, after trying many times and never failing, this was the time it had to fail. Right?
Hello. Yeah.
Bear with us.
I will talk today about my work in which I present a clustering technique within the conformal prediction framework and describe the application to bot-generated network traffic. Hello, I will talk today about my work in which I present a clustering technique within the conformal prediction framework and describe the application to bot-generated network traffic in order to build botnet behavioral models with a view to improving the detection of compromised hosts. A botnet is a malicious network of bots coordinated by a single entity called the bot master. A bot is a malware performing illegal activity based on command received from the botmaster over a command control channel. Botnet can cause a wide range of security threats on the internet, of which the most typical ones are distributed denial of service attack, click fraud, illegal resource consumption, and spamming. Thereby, rapid detection of botnet is of great importance to eliminate security threats rooted in this network, and the first step in this route is identifying bot-infected machine. Methods for identifying bot-infected hosts are divided into two main categories. The first category is host-based method. Used to spot bot-infected hosts by investigating changes occurred in an individual host, such as creating a new file, opening port, or changing computer registry. The second category is network-based method. This method acts as a complementary solution to the host-based detection approaches. In this method, bot-infected hosts are detected by similarity analysis of network traffic by contrasting bot-generated traffic compared to previously extracted behavioral models from malicious connection. This method leverages the observations that bots of a certain family follow similar network behavior pattern in their communication with the command control server, and the relationship between the bot master and bots has a one-to-many pattern. In fact, these two observations define the core network behavior of bots. Network-based bot detection approaches benefit over host-based method in many ways. For example, this approach is scalable, where it is possible to inspect a large number of hosts without the need for any endpoint software installation. My work is of second category, in which by capturing network-level activities of some certain bot families, extracting related statistical characteristics, and using a clustering technique, models of their network communication are developed, and these models are then used in intrusion detection system for botnet detection. In fact, by using a clustering technique, some certain clusters in the data are extracted, and the generated clusters are translated as models of bot's core network level behavior. Actually, the clustering technique I used in my work is an extended version of the multi-level conformal clustering algorithm introduced in previous research in botnet detection. The typical conformal clustering algorithm has a natural connection to hierarchical clustering, where the percentage of objects that are left outside in clusters is regulated by setting up a required level of confidence. In fact, in this context, conformal prediction is used to construct a sequential prediction of possible objects on a grid structure that conform to the using dataset and are not anomalies. The resulting prediction set is then interpreted as a hierarchy of clusters, where a clustering is given by regulating the depth of the hierarchy with a suitably chosen significance level. Also, the work in original paper has some novelty on its own, like applying conformal predictor in a multi-class unsupervised learning setting, plus introducing a neighboring rule for creating cluster from prediction set of objects, but it didn't work well in clustering by producing many small clusters. Moreover, it used purity criterion for clustering performance evaluation, which is found to be inefficient, as this measure doesn't take into account the number of created clusters, and high purity is easy to obtain when the number of produced clusters is large. In particular, maximum purity is achieved if each object gets its own cluster. In my work, an extension of the conformal clustering algorithm is suggested, focusing on clustering where conformal prediction serves to identify a few so-called focal points that are indeed the cluster centers, and adopting an entropy-based conformity measure based on previous work in botnet detection named botfinder. Let us start from the general definition of conformal prediction. Suppose we observe a random sample Z1 through Zn from a distribution P. These are data points in RD. We have a new sample. We also have a conformity measure that represents numerically how much a sample conforms to the previous sample. Conformal prediction is an approach where a conformity measure is used to predict with a level of confidence whether the new sample conforms to the underlying distribution of a previously seen random samples. It is hypothesized that the new sample conforms to the past samples, and this null hypothesis is tested by computing the p-value. In case of conformity, under null hypothesis, a prediction region containing the new sample point with a selected level of confidence is constructed. In my approach, conformal clustering consists of applying the conformal prediction framework to the unsupervised learning task of clustering, focusing on clusters that are defined as a connected component of high-density regions of the underlying distribution. Let's take a closer look. The setting is we have n data point, let's call it z1 through zn. These are some dimensional vector. We also have a density estimator, p hat, which is used as a conformity measure. Let's L bit it be the density level set of the corresponding density estimator. This set is often used for clustering, where by choosing an appropriate value for t, a clustering of the underlying distribution is given. In general, there is no simple way to compute and represent this set. In fact, conformal prediction is used to turn this set into a union of balls or ellipsoid through a grid structure by which a clustering of the underlying distribution is given. By applying the conformal prediction framework, a prediction set consisting of a few so-called focal points that are the centers of possibly overlapping balls or ellipsoid is constructed. So, well, how exactly do I do this? Well, let's say we have a data point. Let's call it z1 through zn. We also have a density estimator used as a conformity measure. The three used conformity measure are nearest neighbor density estimator, kernel density estimator, and the adopted entropy-based density estimator. First off, the data is partitioned into LD grid structure, where L is the number of points per side of the grid and D is the number of features. It is important to note that in partitioning, the number of cells is considered much smaller than the number of data points. Each grid point Z is then considered as a focal point centered at the smallest sphere that contain an effective number of neighbors of this point, where the number of neighbors is controlled by scaling the tuning parameters in the chosen density estimator. We set tentatively zn plus 1 to z. By using the density estimator, a density from the augmented dataset z1 through zn plus 1 is estimated. Then, by applying the conformal prediction, p-value is computed. This process is repeated for each point on the grid, and eventually, conform points to the underlying distribution are obtained with respect to an epsilon, the significance level. And the prediction set C hat, representing a union of balls with 1 minus epsilon coverage, is constructed. In this context, epsilon can be used to trim the outlier or isolated point that cannot form the cluster, while the remaining ones are possibly density connected points that will be in the same cluster. Clusters are obtained by grouping the conform point or focal point in such a way that 2 points which are neighbors on the grid are assigned to the same cluster. In my clustering approach, there are a number of hyperparameters required to deal with, including the number of points per grid size L, epsilon, the hyperparameter for the kernel density estimator, which is bandwidth, H, the number of neighbors, K, if using nearest neighbor density estimator, or sigma, the perplexity parameter in the entropy-based conformity measure. These hyperparameters are of importance because they can correctly identify the true underlying clustering structure. We can systematically organize this hyperparameters tuning process to coverage on the best clustering result, depending on a measure of the strength of cluster, such as index function. As I said earlier, I adopted entropy-based density estimator, which is based on bot finder, previous work in botnet detection. This is the entropy-based density estimator. Here is how it works. In this formula, the similarities between pairs of points are measured P Zi of Zj given Zj measures the similarity between point Zi and nearby point by centering a Gaussian over Zi and computing the density of all other points Zj under this Gaussian. If two points are close together, then P Zi of Cj given Zj is a large value, and the resulting entropy becomes extremely small. That is indicative of highly small pairwise distances. In our density-based clustering approach, this exponentially decreasing measure is of great importance because it simultaneously controls the number of neighbors, size of the cluster, and small pairwise distances. How the cluster is compressed. Moreover, the logic of entropy-based conformity measure is based on the cluster quality rating function in botfinder. In botfinder, each cluster quality is scored based on an exponentially decreasing function, as you see in this slide. Based on this formula, a cluster with larger size and highly similar values gain a higher score than the smaller and sparser cluster. Hence, in this respect, there is consistency between the entropy-based conformity measure and the cluster quality rating function in botfinder. Now, the question is how I am going to apply the conformal clustering algorithm to the problem of botnet detection. I start off by using the TC algorithm to perform dimensionality reduction on the pre-processed dataset created from bot-generated network traffic. The reason why I do this is that the data in the feature space is multidimensional, and this makes clustering difficult due to the possibility of putting each data in a separate cluster. Then the data is separated into training and detection, and the density-based conformal clustering is applied to training set. Once created the cluster, the tested or detection set objects are associated with this cluster. After this, the accuracy of the clustering is evaluated. Before I go to the next section, I need to talk about the way I associate the detection object with the created cluster. Well, once I obtain the cluster, I assign detection set object to them such that for each object Zi in the detection set, we compute its distance to the closest focal point Fji, which is called the residual. For a suitably chosen significance level epsilon, let T sub epsilon be 1 minus epsilon quintile of the residual. We associate Zi with the same cluster at this closer focal point, Fji, where its distance to it is smaller than or equal to T sub epsilon. Now I want to talk about how I evaluate the performance of the proposed clustering algorithm. I evaluate created clusters as the detection model generated during the clustering analysis of botnet malicious connection, both in terms of homogeneity and detection capability. To this end, several criteria are used. Normalized motion information, a measure of cluster homogeneity, is measured the amount of information by which our knowledge about the classes increases when we are told what the clusters are. As I said earlier, in the original paper, purity criterion was suggested for measuring the accuracy of clustering. This is a simple and transparent evaluation criterion. Measure how pure are the clusters. However, this measure can't be used to trade off the quality of the clustering against the number of clusters, and the measure that provides this trade-off is NMI. That's the reason why I select NMI for cluster accuracy evaluation to do with the detection capability of the clustering algorithm. For example, the RAND index penalizes both false positive and false negative decision during clustering. The F measure, in addition, support different weighting of these two types of error. I conducted two experiments to show how much the idea of establishing a connection between a conformal clustering and density-based clustering improves upon the multi-level conformal clustering algorithm, which is hierarchical in nature. Well, in first experiment, I performed multi-level conformal clustering algorithm. To address a multi-level unsupervised layering types of clustering, as previously mentioned, the original paper used conformal prediction in clustering where the percentage of objects left outside of any clusters is controlled by setting up a recoil level of confidence. To this end, it partitioned the training data space into a large grid structure where the training object fall into a position very close to its neighboring point on the grid. Operating on an object distant to its immediate neighbor, it then measured how much a grid point as a new object conformed to the underlying distribution by using the conformity measure, nearest neighbors, and kernel density estimator. Subsequently, conform points to the data set were obtained with respect to the chosen significance level. Conforming points were then clustered using a neighboring rule in such a way that 2 points which are neighbors on the grid are assigned to the same cluster. After this, the detection set data was associated with the resulting cluster where a distance from one of the cluster points is smaller or equal to the grid unit. Moreover, if an object was assigned to more than one cluster, those clusters were made together. Eventually, the algorithm was performed at many levels, with different significance levels, and the suitable epsilon was selected depending on the overall performance. I applied the conformal clustering to the training set with the setting shown in the original paper to achieve the best purity. First table provides the result obtained by the method with kernel density estimator and nearest neighbor. The first column G gives the true number of clusters. The second column G hat gives the estimated number of clusters. As it is showed, the conformal clustering algorithm didn't work well in clustering. It is worth noting that in this method, conformal prediction is used to construct a sequential prediction set on a large site grid. Thus, the training option falls into a position very close to its neighboring point on the grid, thereby constructing a prediction set with the first nearest neighbor and kernel density estimator with a too small bandwidth that is shown to achieve the best result without considering cluster as high-density regions of the underlying distribution, would make the grid point conformity more likely, even when that point falls into a position very close to an outlier. Besides, this approach led to producing portion of the feature space trimmed by the chosen significance level, which is an additional workload. In the second experiment, I applied my approach to the corresponding training set. The second table gives the best result obtained by my approach with a good setting for the corresponding hyperparameters. As I said earlier, there are hyperparameters that I have to deal with, including the grid site, L, epsilon, and the corresponding hyperparameter in the use conformity measure. To tune this hyperparameter, it is required to select a set of values on an appropriate scale to explore the hyperparameters. To this end, I randomly sampled the point accompanied by a coarse-to-fine sampling scheme and try the corresponding hyperparameter on this randomly chosen set of points, and then pick whichever hyperparameter lead to the best clustering result. By comparing these two tables, it is understood that my approach improved upon the typical conformal algorithm, both in terms of accuracy and detection capability. For future work, I'm going to investigate the efficiency of you bringing together conformal prediction and some famous density-based clustering algorithm such as DBSCAN, and propose an unsupervised machine learning approach for botnet detection based on the underlying algorithm of bot finder by using the entropy-based density estimator. Thank you.